Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on 120 degrees conduction mode of three-phase inverter. In the previous lecture, we have covered voltage source inverter. In the voltage source inverter, single phase, half bridge and full bridge inverter. In that R load, L load, RL load, RLC load, in that XL is greater than XC and XC is greater than XL. The same for full bridge inverter. Next, three-phase inverters. For the working of three-phase inverter, there are two possible modes. First one is the 180 degrees conduction mode and second one is the 120 degrees conduction mode. In the 180 degrees conduction mode, each thyristor conducts for in the segment 180 degrees, and in the 120 degrees conduction mode, each thyristor conducts for 120 degrees only. Remaining 60 degrees duration, no thyristor will conducts. In this lecture, we are going to discuss 120 degrees conduction mode of three-phase inverter. So now let us see the circuit diagram for 120 degrees conduction mode three-phase inverter. In this circuit, we have total 6 thyristors, 6 switch SCRs. So total switches 6 SCRs, and next here 3 legs. Legs may be a segments, arms, wings. So that are 3 legs. And next here total groups. Total groups are 2 groups. Total 6 thyristors, T1, T2, T3, T4, T5 and T6. T1, T2, T3, T4, T5 and T6. Total 6 thyristors, 6 SCRs. So these are acts as the switches, turn on and turn off. And next 3 legs. So leg 1, leg 2, leg 3. In the half bridge inverter, we have only 1 leg. In the full bridge inverter, we have 2 legs. In the three-phase inverter, we have 3 legs, 3 wings, 3 arms, 3 segments. Now, here in the first leg 1, T1 and T4. In the leg 2, this is leg 1, leg 2, T3 and leg 2, T3 and T6, and leg 4, leg 3, T5 and T2. And here there are 2 groups, upper group and lower group. Upper group switches are denoted as T1, T3 and T5, and lower group switches are T4, T6 and T2. And here one DC source and one load. Here the load is balanced star connected load. Here we have total 6 assumptions. Here first assumption, here first one, snubber circuit and commutation circuit for thyristor switch SCR. So for the simplicity purpose, so this circuit must be avoided. So snubber circuit and commutation circuit should be omitted. And next here the load may be either star or delta, balanced star or delta. Next, this is first and this one is the second and this one is a third assumption. Third assumption means in the each leg, in the same leg, sorry, not each leg, same leg, both the switches at the same time should never be closed. So T1 and T4 should never be closed. T3 and T6 should never be closed, and T5 and T2 should never be closed. At the same time, 2 switches, both the switches in the same leg should never be closed. It may lead to the battery short circuited, VDC. It may lead to the battery short circuited. So that may failing the entire setup. And next, so all the time it should be avoided. And next, in our So in the each leg, in the each segment, each arm, each thyristor conducts for 120 degrees only, not 180 degrees. So now here first in the each leg, first leg, this is row for leg 1, row for leg 2 and third row for leg 3. Leg 1, leg 2 and leg 3. So T1 conducts only for 120 degrees 120 degrees duration only. Remaining 60 degrees conduction, no thyristor will conduct. None of the thyristor will conduct. Next, T4 will conduct. In the each switch, in the each leg, only switches will conduct only 120 degrees duration only. Next, this is fourth assumption, and fifth assumption. In order to get the balanced three-phase output voltage, each thyristor in the upper group thyristors conducts at an interval of 120 degrees only. Here, what are the upper group switches? T1, T3 and T5. T1 starts at 0 degrees and T3 starts at 120 degrees and T5 starts at 240 degrees. Each thyristor in the upper group T1, T3 and T5 conducts at an interval of 120 degrees apart. The same for lower group switches T4, T6 and T2. So this I will explain in the next slide. So these are the total 5, fifth one. So because we are dealing with three-phase output voltage, next, at any given time there are only 2 switches will conduct. So here if you see this, at any given time only 2 switches will conduct. In the previous case 180 degrees conduction mode, 3 switches will conduct. At any given time, one from upper group switch will conduct and other from lower group switch will conduct. Now let us understand the control scheme for this 120 degrees conduction mode. How each thyristor will conduct, that we will see. First, T1 in the leg 1, this is leg 2 and leg 3. So leg 1 for row 1, leg 2 for row 3 and leg 3 for row 3. Now here first T1 thyristor in the first leg, so this is leg 1, the first leg T1 thyristor conducts. So here assumption number fourth one, I think fifth one. So fourth one, so each thyristor conducts for only 120 degrees case. So here T1 conducts up to 120 degrees only. So remaining 60 degrees, none of the thyristor will conduct. So this will be vacant. And next thyristor is T4. T4 will conduct for 120 degrees only. Remaining 160 degrees duration, no thyristor will conduct. And next here, in order to get the balanced output voltage, so upper group switches conducts 120 degrees apart. So T1 starts at 0 degrees and T3 must start at 120 degrees only. So if you see here, this is T3 must start at 120 degrees only, 120 degrees apart, and after that each thyristor will conduct only 120 degrees. Remaining 60 degrees it will be vacant. So T3 conducts up to 240, 120 degrees only. The duration time for each thyristor in 120 degrees conduction mode in the 3-phase inverter mode is 120 only. And next, this is vacant. And next, here what is the thyristor? Here the lower group switch is here T6. So T6 thyristor will conduct. Next, T6 conducts only up to 120 degrees only. Up to here it will conduct, and remaining it will be vacant. Next, third leg In the third leg switch, upper group switches are T5. So T5 must start at 240 degrees because T3 and T1, T3 and T5 conducts at 120 degrees in order to get the balanced output voltage. We needed the output terminals at output terminals balanced three-phase output voltage. So here T5 must start at 240 degrees. And next, up to 240, 240 plus 120, 360, this will be vacant. No thyristor will conduct. And next, here, next thyristor T5 and next in the leg 3, T2 SCR. T2 thyristor should be started at 60 degrees. So it will be 120 means this is T2 and next this one should be vacant. This is the control scheme of 120 degrees conduction mode of three-phase inverter. Thyristors are programmed to turn on and turn off in order to get the balanced three-phase output voltage at the output terminals. Now, in the last assumption, sixth assumption, at any given time, only two thyristor will conduct. So 0 to 60 degrees case, T1 and T6 will conduct. T1 is from upper group and T6 is from lower group. Same way, 60 degrees to 120 degrees case, T1 and T2 will conduct. So T1 from upper group and T2 from lower group. Same for 120 to 180, T3 and T2 will conduct. T3 and T2 will conduct. T3 from upper group and T2 will from lower group. So in this way, so at any given time, only two switches will conduct. In case of 180 degrees conduction mode, only three switches will conduct. So this vacant position also another conductor will conduct. Now, during 0 to 60 degrees case, what are the phase voltages? So that I will explain now. So 0 to 60 degrees case. How we can draw the equivalent circuit? 0 to 60 degrees case. 0 to 60 degrees case, only T1 and T6 two thyristors will conduct. T1 and T6. So T1 thyristor will be closed and T6 thyristor will be closed. And this is connected to negative terminal of the battery. And next, this is connected to N and this one and this one. This is A, this is A, this is B. So this is A and this is B. So B is connected to through Z. This is B is connected to through Z. This is N. From the B, E. So this diagram, so from battery positive terminal and negative terminal, positive terminal of the battery is connected to the T1 switch. So T1 switch is closed, short circuited, and Z, A through A. After that N, and next this one, this one, this one, and it is negative terminal of the battery. So now here from this you can determine the phase voltages VAN and VBN. So now here we know the VDC and there are two same balanced star load connection here. So Z and Z. So by using voltage division rule, we can determine this VAN and VNB or VBN. Voltage division rule we know very well. So here VDC equals to VDC into Z by Z plus Z. So this value is Z by Z plus means this is 1 by 2 VDC by 2 VAN value. Voltage division rule. supply voltage into same branch voltage divided by same branch impedance divided by total impedance. Same branch impedance Z and total impedance is Z plus Z. So that value is Z by 2, VDC by 2. And what about VBN value? Not VBN. So this is VDC by 2. And if it is VDC by 2 means this value is also same VDC by 2. This value is VDC by 2. So now here VNB equals to, this is VAN and this is VNB. So that is also VDC by 2. But we need phase voltage VBN. So VBN means, so that value equals to minus VDC by 2. Minus VDC by 2. So now what about the VCN? We need 3 VAN, VBN, VCN. So VCN value is 0. There is no connection here. So that value is 0. VCN value is 0. So now VAN, VBN and VCN. Same thing for 120 0 to 60 degrees to 120 degrees duration. So that I will explain. So 60 to 120 degrees duration, what are the thyristors will conduct? So T1 and T2 thyristors will conduct. T1 and T2. So now here T1 thyristor will conduct and T2 thyristor will conduct. So T1 is connected to positive terminal of the battery and T2 is connected to negative terminal of the battery, and this is connected to this neutral and this is connected to this one. Now here same, this is A and this is C, and next this is neutral, and next this is negative terminal, and this is a positive terminal. This is T1 here, this is T2. That are short circuited. Now same thing, same formula, voltage division rule. Here you can VAN equals to VDC by 2, already we discussed, and this VNC equals to VDC by 2. VDC by 2, and this is VCN is minus VDC by 2. And what about VBN? VBN value is, there is no connection for this leg. So now here this value is VBN equals to 0. Next, during 120 to 180 degrees case, T2 and T3 thyristors will conduct. So T3 and T2 thyristors will conduct during 120 degrees to 180 degrees. Now here 120 degrees to 180, T3 and T2. So T3 short circuited and T2 short circuited. And here, so this is this one, and next this is connected to here, next this one is connected to here. Same thing here, this is B and this is C. Here VBN value, VNC value, VDC by 2. VCN equals to minus VDC by 2. And what about VAN value? There is no connection for this first leg. So this VAN value is 0. And next thing here, 180 to 240 degrees case. 180 to 240 degrees case, T4 and T3. So that T4 and T3. T4 is here lower group switch, first one in the first leg, and next upper group switch leg 2. So this is connected to positive, and next here this is connected to negative. This is here and this is connected here. This is B and this is A. Same fashion, voltage division rule, VBN equals to VDC by 2 and VAN equals to VDC by 2 and VAN equals to minus VDC by 2. And what about the VCN value is 0, no connection. Next, 240 to 300. So T4 and T5 thyristors will conduct. What about T4 is connected and next T5 is connected to this one. And here this one is connected here to this neutral and this one is connected to here. These are the. Now here same voltage division rule. This is VC and this is VA. So VCN is VDC by 2, VAN equals to VDC by 2, VNAN equals to minus VDC by 2. And what about this VBN equals to 0. Next, last one is 300 to 360 degrees. T6 and T5 thyristors will conduct. So now here T5 and T6 thyristors will conduct this one and this is connected to here. This one. This one. This is plus and minus, plus and minus. This is C and this one is the B. Now here VDC, VCN is VDC by 2 and VNB equals to VDC by 2 and VBN equals to minus VDC by 2. So what about the VAN? This is 0. Now each duration from 0 to 60 degrees case VAN value, VBN value and VCN value. This is VDC. And next here 0 to 60 degrees VDC and minus VDC and VBN. So 3 phase voltages 120 degrees to 180 degrees. So 3 phase voltages VAN, VBN, VCN. 180 degrees to 240. This is VDC. 240 to 300 VAN, VBN, VCN. This is VDC. 300 to 360 VAN, VBN, VCN. So now we have all the phase voltages during 0 to 60, 60 to 120, 120 to 180, 180 to 240, 240 to 300, 300 to 360. Each interval at 60 degrees interval, we got the all phase voltages. From this, we can plot the phase voltage waveform diagram. So now here, this is our 120 degrees conduction mode, 3-phase inverter control scheme, and these are the phase voltages according to that equivalent circuit and that each leg thyristor turn on and turn off. If you plot the phase voltages are represented with VAN, VBN and VCN. Now VAN value is VDC. Duration I will mention here. These are the durations 60, 120, 180 durations. So now this according to this phase voltages, we can draw the voltages. So now if you see this waveform carefully, VAN is VDC by 2. This is VDC by 2. And next, this one is VDC by 2. And next here, this value is 0. And next here, this is minus VDC by 2. Minus VDC by 2. And next here, this is also minus VDC by 2. And this is 0. This plot is over. And next VBN. this is minus VDC by 2, and next case VBN is 0, and next case here this is VDC by 2, this is one is also VDC by 2, and next here this is 0, and next here this is minus VDC by 2. And next VCN is 0, this is 0, and next minus VDC by 2, VDC by 2, minus VDC by 2, and next this is minus VDC by 2, and next this is 0, and this one is VDC by 2, and this is VDC by 2. This is the phase voltage diagram for VAN, VBN and VCN. Now let us plot line voltage diagram. Line voltage diagram. This is our phase voltage diagram. Line voltage means here line voltages are represented VAB, VBC and VCA. VAB means VAN minus VBN. VBC means VBN minus VCN. And VCA means VCN minus VAN. So now here subtract from VAN, subtraction only. From the phase voltages we can determine the line voltages. Now here this is VDC by 2 and this is VDC by 2 and this is minus VDC by 2. VAB. VAB means this one minus this one. VDC by 2 minus of minus VDC by 2 means if you draw the plot here, this is VDC by 2 minus of minus V. This is VDC only. VDC only. After that, this is VDC by 2 and this one is 0. This is VDC by 2. And next, this is 0 and this is VDC by 2. This is minus VDC by 2. This is minus VDC by 2 and this is VDC by 2. Minus VDC by 2 minus VDC by 2 means that is minus VDC. And next this is minus VDC by 2, this is 0 minus VDC by 2. And this 0 and minus VDC by 2, that is plus VDC by 2. So first VAB line voltage waveform is this one. And next same fashion for VBC means VBN minus VCN. VBN minus VCN means this is minus VDC by 2 minus 0. This is 0. Sorry, not 0. Minus VDC by 2. And this is 0 and this is minus VDC by 2. That is positive VDC by 2. This is VDC by 2. This is minus VDC by 2. So that is plus VDC only. Next, this is VDC by 2, this is 0, this is VDC by 2. This is 0 and this is VDC by 2, that is minus VDC by 2. And next here, this is minus VDC by 2 and this is VDC by 2 minus VDC. And next, the last one VCA means VCN minus VAN. VDC by 2 minus 0, sorry, 0 minus VDC by 2, that is minus VDC by 2. And next here minus VDC by 2 minus of, this is minus VDC. And after that minus VDC by 2, 0 minus VDC by 2. Next here 0 minus of minus VDC by 2 plus VDC by 2. And next here this one VDC by 2 minus of VDC, this is plus VDC. And next VDC by 2 minus 0 VDC by 2. And next These are the phase voltages and these are the line voltages. From the line voltage waveform, from the phase voltage waveform, we can determine the RMS value, phase RMS value and line RMS value. So now here, this is VDC by 2 and this is minus VDC by 2. So we have seen the phase voltage diagram. So now here, from this waveform, we can determine phase RMS value. How you will determine the RMS value? So we already discussed, we know very well this RMS value. Square the waveform, okay, na? Take the under root. So now here, so if you take this only half cycle, you can take, this is symmetrical waveform. So if you square it, so no problem, take the 1 by pi. So this is VDC by 2 whole square. This is up to 2 pi duration and this duration is 0. This value is 0 means 120 to 180 degrees value means that value is 0 under root. So this V phase RMS value equals to pi gets cancelled and 2 and this is 2. So VDC by root 6. So in another way also we can determine. So this is under root 1 by 2 pi, this value that 0 to pi. So VDC by 2 up to 2 pi by 3 whole square, this one duration, and next here pi by 3 duration, this pi by 3 duration, so this value is 0, and next plus this one is whole square, so this value is VDC by 2 minus VDC by 2 whole square, so that one is by 2 and 2 pi by 3 plus VDC by pi by 3 and this value is 0. So same thing you will get. So this phase RMS value equals to VP RMS VDC by root 6. So now here line RMS voltage we can determine easily. We know very well VL equals to root 3 V phase. In the 3-phase circuits we discussed there is a relation between phase voltage and line voltage. Line voltage equals root 3 into V phase. So now if you multiply with root 3 you will get directly VDC by root 2. Otherwise you can determine from the line voltage waveform also. This is VDC, this is VDC by 2 and this one is, this is root VDC by root 2. So line RMS value, phase RMS value we determine. So now here from the formula also you can determine up to take the half cycle. So this is symmetrical. So now here, so up to this one 5 by 3, 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 5 by 3. This is VDC and this is VDC is VDC square and next this is VDC square, VDC by 2 minus VDC by 2 square means that is positive. So if you simplify it also this value is same VDC by root 2. Next, switch current. So thyristor current equals to, this is VDC by Z. So that value is, if you take the switch current RMS value, so 1 by pi. So it up to 2 pi it has considered. So that is in the previous case that is up to consider 1. So that is VDC by root 2 Z. Now what about the power? For star load VL equals to root 3 V phase RMS. So V phase RMS equals to VDC by root 3. We derived output power equals to 3 into V phase RMS square by Z. Our output power equals to that current square into R into 3. For delta load same, VL equals to VP, that means line voltage equals to phase voltages. So line voltage and phase voltage is same for delta load. These are the formulas. So this is regarding power. I hope this 120 degrees concept is clear to you. If still have any doubts in this lecture, You can comment in the comment section below. I will answer to your queries. Thank you. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.